So today's chapter is about gain scheduling. What's scheduling means? Let's see an example. Let's take this pendulum example. We all know pendulum, and we all know that it is a nonlinear system. If I ask you to find for the pendulum the torque, the transfer function, torque over theta, you could not find it. If I ask you Ts over theta of s, you cannot find it, because transfer function can be found only for a linear system, and this is a non-linear system, unless if you linearize it around an equilibrium point. Could be this theta as an equilibrium point, could be this theta as your equilibrium point, could be that theta as the equilibrium point for you. So then, for each equilibrium point, the pendulum have different dynamics. Depends on the angle you are taking. The pendulum have different dynamics, and it is valid only around this zone. So the dynamics is valid around a small zone, because it is we linearize around an operating point. Usually we linearize it around 180 if it's inverted pendulum, simple pendulum around 0 degree. Alright, and we use then, that means for this simple system I can have different dynamics depends on theta. So what now if I challenge you and ask you, can you design for me a controller in which you want to control the pendulum around 0 degree, should oscillate only around 0 degree? Means what? Means now if I come and I put a disturbance, it should stay at 0 degree. If I push it a bit, it should return back quickly to 0 degree. So imagine it is here. If it's not controlled, if I push it, then it goes, maybe it keeps oscillating for a long time before stabilizing itself. If you have an actuator here and controlling it, even if you push, then it should return back quickly by rejecting the disturbance. Your controller can reject the disturbance. Okay, so what if I ask you to control it to stay at this angle, like 45 degree? Saying you can linearize it around a 45 degree, find a transfer function around a 45 degree, and get a different PID controller for angle theta 1. What if I angle theta 3? If I tell you this is angle theta 3, I want theta 3 to be my operating point. Means the controller should always, the pendulum should be fixed here, following my reference. So now if it is here, if I disturb it, it should return quickly to here. Then this will only be valid if I get a linearized model at theta 3, and then based on this linear model, what I do is I design a controller corresponds to this angle. And now I have 3 controllers for 3 different positions. If I want at every position, then I need many controllers. What I'm actually doing is the following. What I'm doing actually, I'm designing PID 1 for theta 1, PID 2 for theta 2, because for theta 1 you have a transfer function 1 dynamics different than the dynamics of the pendulum at theta 2. Okay, this is theta 1, assuming this is theta 2. And also at theta 3, you will have different dynamics, therefore you will get different PID. Then what we mean by different PID? Then you will get different KP, KI, and KD. Then you are scheduling, you are varying your gains, depends on the dynamic of the system. And that's what gain scheduling is about. Gain scheduling is to control non-linear system like this pendulum using linear techniques, using transfer function. which is a linear technique, by testing theta. If theta equal my theta 1, then use the gains corresponds to PID 1. If theta equal theta 2, then use the gains for the PID corresponds to uh, that I found for the with the transfer function f2, etc. That's what we mean by gain schedule. Okay, so it's to control non-linear system like this using a linear technique like transfer function, which is a linear technique. Alright, so keep in mind you cannot find a transfer function of a non-linear system unless if you linearize it around an equilibrium point, which is your equilibrium point in this case could be theta 1, theta 2, theta 3, etc. So this is like typical academic example, but you can find also some industrial example in aerospace engineering, for example. This is a non-linear system. The airplane is a non-linear system. So here you have two variables, at least two variables, they are affecting the dynamics of the system. So then the speed of the relative speed of the airplane with respect to air, this speed of the airplane, if it change, the dynamic of the system will change. The incidence angle alpha, if it change, also the dynamic of the system will change. Now here I have only one variable, which if it change, the dynamic of the system will change. Here I have two variables, alpha and v. So therefore, assuming I'm designing, I have only proportional controller, so then my proportional controller value of it could take different values depends on alpha and v. So then you need to have a program checking alpha and v, and each time for each alpha and v you having one gain, so you get this kind of gain. So if alpha and v are here, so then this should be your gain. So then you're gonna switching gain based on your dynamics. Okay, what we are doing is, and how did we find this gain? Also we did a linearization of the system around alpha and v, alpha 1 v1, alpha 2 v2. At each operating point, here my operating points are alpha 1 and v1. At my operating point I designed I linearized the system at the operating point, and I tuned my controller to get the gain. And then at different operating point I get different gain, etc., etc. Okay, here that's what he's saying. Linearize model at multiple operating points. Design a linear controller for each operating point. For theta 1, design a linear controller. Theta 2. For alpha 1 v1, design a controller. For alpha 2 v2, design, etc. Interpolate the set of linear controller into a single controller. Okay, that's the third step. That's the workflow of gain scheduling, and that's what gain scheduling is about. Okay, if you wish, you can search for it online. Like, well, it's a French tutorial. It's not the only tutorial exists, of course. You can find others like here, very similar, but in English, not exactly similar, so different person. Automatic tuning of gain scheduled controller. You can look at it. This is also another example. So now we saw two examples of nonlinear system. I'd like also to show you one more example that you can find lot of nonlinear system. Any nonlinear system you can do it this way, or any time varying system. Like a system varies with time. Okay. So here is two typical example. In process engineering control, you can find also some other example, like here. Maybe you can take this example. I'd like to explain the example a bit, but the idea is the same. You need to do gain scheduling. Okay, If the system is nonlinear, we do gain scheduling, and exactly the process will be as defined here. Linearize model at multiple operating points. Design linear controller for each operating points. Those are the two main important points. Later on we'll see the third, it's alright. But those are the points that I want you to know. Linearize the model at multiple operating points. So means you will be having different money transfer function 1, transfer function 2. Also you'll be having many models of your system. Each model represents a dynamic at a given operating point. Okay. Then we design the linear controller for each transfer function. Alright. Here I'm with the same person, but just I switched to the end to show you this example. This is a good example in process engineering. So you have a chemical reaction that happens here, in which you have a chemical A or material A want to be converted to material B. Okay, that's a chemical reaction that happens, in which you are feeding concentration, feed concentration from some material, maybe from some concentration from some material at a given temperature. So here you are feeding to your system TF and CF. Those are not design parameters, those are feeded constant, are not control parameters. And you have a sensor that measuring for you the residual concentration CR of material A and the reactor temperature TR. How much is, so I have a sensor that measuring me the concentration and the temperature for the reactor. Like TR like reactor temperature, CR like residual concentration. So I have a sensor that measuring me these two output in blue. These are my output. I have a sensor that measuring them to me. Residual concentration of material A and reactor temperature. What is the temperature? And my only control input is in blue here, the coolant temperature or TEC. Coolant temperature is my only control input. So this is the input of the system that I may control it later by having control. Okay, that only I can control the coolant here, the temperature of the coolant which is here. It's something I can control it. Okay, this is a desired scenario. Decreases residual concentration A. For material A, that's what should happen. What's desired is to reduce A to end up having only concentration of B. If initially I have a maybe 100 concentration of A or whatever it is, then I expect it will reduce. That's the desired scenario. Decrease residual concentration. So here I'm measuring the residual concentration. I must probably go ahead and feed it back. Okay, and if it is negative, I compare it with, if it is negative, you like to have it this way. Okay, I know. So okay, negative feedback, and here your reference is, let's say, the desired concentration, reference concentration also, and this is my reference, so I'm comparing it with your reference concentration. Here you get the error. Your reference, you want to decrease the concentration of A. Okay, in a way maybe I have controller here that control the temperature for me. How the concentration of A, the way it decreases depends actually in the cooling jacket which is here. Depends in the heat inside. How much is the temperature degree here, so we can know how fast we decrease. This is some chemical reaction. So I'm introduced it to you just to understand it. And this system is a highly nonlinear system. And therefore its nonlinear system So how to find PID? Well, PID, I need to linearize the system. Very nice. But if I linearize the system at a given operating point, it doesn't work at different operating points. It turns out, this is my point that I want to tell you, it turns out that the dynamic of that system, here, the chemical reactor, the dynamics of it depend on the concentration of A, on the residual concentration of A. So like if assuming it is 10, it is somehow like equal to that value, like, okay, assuming this is more CR1, okay, CR2, CR3, CR4, etc. At each CR, at each residual concentration, the dynamic different. So you can get different transfer function for your plant, for your chemical reactor. Okay, for this chemical reactor CR, well, for this chemical reactor, it has different models, different dynamics, depends on CR. So then how to control it? How to find the PID? So then what you need to do, you need to extract 1, 2, 3, 4, 5, 6 model, assuming you need to extract 6 model, linearize them around 6 operating point, which is the value of CR1, CR2. So here. So you linearize them around this point, and for each transfer function you find the gain of your PID. Okay, you find the gain of your PID, and then you need to implement an algorithm saying if you measure here the CR, if CR equal to that value, then switch to different gain, etc. So then that's what we call gain scheduling. You are changing the gains of your PID depends according to the change in the dynamics of the system. Otherwise, if you don't want to do that, then do a nonlinear control, but we didn't take nonlinear control yet. So then, if we want to control a nonlinear system using linear techniques, transfer function, for example, you need to do gain scheduling. Okay, so as in this system, we'll see it in as a MATLAB tutorial later. So this is what gain scheduling is about. Right. So I have here a video for you. This video link, it is here. It is here. Okay. So you can write control system in practice. What is gain scheduling? 14 minutes video. It's guided video, so you can look at it if you wish. But in general, gain scheduling is already introduced to you. Nothing more to say. So as I said here, so for each operation condition you may get different dynamics, and therefore you need to change your tuned gain, because this transfer function, whatever gain work for this transfer function doesn't work for this transfer function. Alright, so imagine like you are in an airplane in which you have Mach number, then the dynamics depends on the Mach number, depends on the dynamic pressure, depends on the force, the center of gravity, etc. So then for each scenario you have different PID. Okay, and the trick is, which is this point, which I didn't explain yet, the third point here. So what's the problem now? This third point telling you like, well, so this unwanted behavior, we'll see it here in a few minutes.
Some value, use gain set A. If it's greater or equal to that value, then use gain set B. Now this is
Okay, so this explained in a while. So you change the gain depends in the desired operating point. Okay, scheduling variable basically, it's so often it's your operating point at which you are linearizing the system. If now you are at theta 1 or at some pitch angle, so this pitch angle corresponds to maybe a gain equal to a set of gain equal a, the other pitch angle maybe a set of gain equal b.
an attractive architecture because of how simple it is to think about and implement. However, it produces some unintended transients when the switch occurs.
So when the switch occurs, this technique produce unintended transient behavior. What is it about? What is this?
To understand how this can happen, imagine the following situation. Instead of a PID controller, let's say we can get away with just a proportional controller. That way there's only one gain value. So we have two design points in our gain schedule. A gain of 3 when the Mach number is above or equal to 0.5, and a gain of 2 when the Mach number is below 0.5. Initially the aircraft is at 0 degrees pitch, and we command the autopilot to pitch up to 10 degrees. The aircraft is flying at Mach 0.6, and as the aircraft starts to pitch up, it's using a gain of 3 accordingly. And as the plane continues pitching up, the speed starts to drop. And right at Mach 0.5, let's just say that the pitch error is 5 degrees. We're not at 10 degrees yet, and so the output of the controller is 15 since there's a gain of 3 and an error of 5 degrees. At the very next time step, the Mach number drops to 0.499, just below the threshold, and the gain set switches instantly to 2. The error hasn't changed much in this amount of time, so it's still about 5 degrees. Therefore, the output of the controller jumps down to 10.
So the output of controller jumped from 15 to 10.
And this would cause a quick motion of the elevator, and the aircraft would quickly change its pitch.
Because now you are giving your actuators very small value.
Startling the passengers and spilling their drinks. So
So this is uncomfortable for the passenger. So in his example, he's giving the scheduling variable his operating condition. In this case, is the Mach number. Mach number is the scheduling variable, not necessary. Sometimes it is your desired reference, is your desired operating point. Like inverted pendulum could be your reference angle, right? As example, it could be something else. Like here, the operating point, in this case, it's your scheduled variable, which is the Mach number. Depends on the Mach number, the dynamic change. Like the example I show you before, alpha and V for the aircraft, maybe theta for a pendulum, etc. This is undesired behavior, and this transition um, we can take rid of it by using a surface of value. Like instead of moving from 3 to 2 directly, we can have a polynomial, maybe linear or quadratic polynomial, or yeah, something like. So you have smooth transition from one gain to the other by creating a surface. Okay, this as interpolation here. That's what he called. Sorry, that's what that guide called here. Interpolate the set of linear controllers into a single controller, like having a surface of, okay, instead of one point, having a surface. Yeah, that's it for introduction. Now let's start in action.